Hello. Nice to meet you.
Me too.
Okay, so I'll do the presentation and
Okay.
then I'll give you the right to share. Okay, so welcome everyone to this webinar series organized by our research center, it's the Language Technology, the Basque Center for Language Technology. And this is organized in conjunction with our Deep Learning for NLP course and our Master on Language Technologies. We had an exciting lineup of researchers talking about hot topics, and you can check all the recordings of the past speakers in the webinar website. So today is my honor to introduce Sakriani Sakti. She is currently holding several positions, both in Japan, in two institutions, HIST and NIST. She's also a visiting research scientist at Riken and an adjunct professor at Indonesia. She has been working on spoken language communication laboratories and the dialogue system group in several countries. And I think most importantly, she was involved in creating the joint ELRA and ISCA special interest group on under-resourced languages. And she's in the board since 2018. So without further ado, I welcome Sakriani Sakti, and please go ahead.
Okay. Hi. Good afternoon, everyone. So thank you again for inviting me to this HITS Language Technology webinar series. And thank you very much for the nice introduction. So let me share my slide. Okay, can you show my slide?
Yeah,
Can you see?
they look great.
Let me just check.
I'll be back. Hasta la vista.
Okay, can you hear the sound?
Yes.
Okay. Okay, great. So let me put it here somewhere. Okay, so in this webinar, I will talk about our recent work, which is about semi-supervised learning for low-resource multilingual and multimodal speech processing with machine speech chain. And of course, this work is not done by me alone. So we have a team. So this work mainly I did at when I was in NICE and Rikeng AIP, and I moved to JAIS last year. So the team include Andros Chandra, Johannes Effendi, Sasi Novitasari, Saoko Nakayama, and Satoshi Nakamura. Okay, so okay, in human-to-human communication, speech is the most natural modality to express our idea, experience, and knowledge. So usually we use everywhere during meeting, business, lecture, and conversation. And in 1993, Dance and Pinson defined what is called a speech change mechanism. So this is the mechanism for human-human communication, where the message is transformed from the speaker mind to the listener mind. So usually what happens is that the speakers start to think in their brain what the word they want to say. So this is, we call it in the linguistic level. Then after that, they articulate the word with the vocal tract and the mouth and everything. So this is physiological level. And finally, the speech waveform is transformed to the air, which is acoustic level. And finally, it's received by the listener with the auditory mechanism, which is again physiological level. And then finally, the message come to the brain, which is again linguistic level. But there is this point, which is auditory feedback. So this means that there is from the speaker mouth to his own ear. So when speakers say, the message is not only received by the listener, but he himself can hear what he said. And this is quite important during communication. So I will explain this later. So when we want to build the human-machine interaction, one of the earliest objective is to realize a technology or machine that can communicate with humans. So we want to replace from using like keyboard or mouse to a machine that can use a speech communication like a human. So what we do here that we try to replace this with a machine, and then we try to provide a technology that has ability to listen by way of speech recognition and the technology that can speak by way of speech synthesis. And we know that there's a lot of research that have been working on ASR and TTS. For example, for ASR, start from the rule-based to the hidden Markov model, and then now we use most of the system use the deep learning. So the important factor of deep learning is can simplify many complicated hand-engineered models, so then it let the network find the way to map from speech to text directly. And the performance also have been improved significantly. As we know that recently, I think it's 2017, Microsoft has claimed that the speech recognition has reached or make the same or fewer errors than the professional transcription is. So here the Microsoft system, if reads with the switchboard data, reads error rate like 5.8 error rate, while the human transcription is 5.9. And then not longer after that, IBM claimed that their system can even further to decrease the error to 5.5 error rate using more sophisticated language model. And the same way on the TTS side, from the unit concatenation, hidden Markov model, and again, it's also the same with the deep learning. And also the quality, like if you hear that in the past, the sound is really like a robot voice.
I'll be back. Hasta la vista, baby. Arnold Schwarzenegger's Teutonic drone in the Terminator films is world famous.
So now it's more like a human voice.
I'll be back. Hasta la vista, baby. Arnold Schwarzenegger's Teutonic drone in the Terminator films is world famous.
And even recently, Google Duplex built a system. So usually, the machine become like agent that help human to do something, but Google Duplex tried to be the user who tried to. So this is Google Duplex tried to call a restaurant and order a food. So I will play. So the sound of the man is the machine.
See, how may I help you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people? When? Today?
Next Wednesday at 6 p.m.
Oh, actually, we reserve for like upper like 5 people. For 4 people, you can come.
Okay, so as you can see that maybe in the future we have no idea which one is the human, which one is the machine, because they are now really look alike. So looking at this, what is left? Are all problems solved? I mean, because the speech recognition already better than human, and the TTS already also similar like human. So what else that we can do if this solved? The problem is the learning issue. So in order to reach such quality, we need a lot of data. It's always data hunger, and especially it requires a lot of parallel speech and text in order to build speech recognition and speech synthesis more than the human need. And the problem is such data is often not available. So if you see this language of the world, so this is one dot is a one language, and we have approximately like more than 7,000 living language. Up to now is only maybe in maximum like up to 100 languages that are covered by language technology. So means that nearly 7,000 living languages spoken by 350 million people have not been covered. So how we should do there? If we keep with using the current technology, it's difficult to build for those languages. So why the machine needs so much data? So let's see how the human do the language learning. So the baby infant, when I think before 1 year, they are do bubbling. This is kind of like unsupervised learning. They do bubbling. After that, they have a feedback loop with the mothers. So for infant to start producing their first word, they must first begin matching the sound of babble and the sound of the caregiver. So they need, in order to say something, they need to listen and then matching and then over and over. And even when there is no parents or caregiver, the toddler can continue learning how to talk by constantly repeating their articulation and listening to the sound produced. So again, this is because we humans have the critical auditory feedback mechanism. So we can speak and we can listen by ourselves. And then after that, we can repeat it, we can correct it, and then do it again and again. So for example, for the baby or toddler that have hearing loss, meaning that they don't have no auditory feedback, they often have difficulty to produce the clear speech. And even adults who become deaf after becoming proficiently with a language and will suffer speech articulation decline as a result of the lack of auditory feedback. So in the study in the brain science, Hickok also found that there is activity that exhibit here in the brain that activated both during the perception and also during the speech articulation. So he found that the auditory system is critically involved in the production of speech, and the motor system is critically involved in the perception of speech. Now, let's see how the machine learning do. Machine learning, for learning how to listen, we build speech recognition. And when learning how to speak, we build speech synthesis. And the learning to listen and speak are done separately and completely independent. And more, the problem is that the computers cannot hear their own voice. So even they claim that they already reach like better than human, but they even cannot hear their own voice. They don't know what they output, and they don't have the feedback of that. So because of this done separately, it means that we need to, so for ASR to map from speech to text, it needs a correct text transcription, right? And also for TTS, in order to map from text to speech, TTS require the truth of the speech waveform in order to calculate the loss. So because of this, and that's why they need a lot of parallel speech and text data, and such data is difficult to achieve. So that's why we try to construct message speech chain, and the time is 2017. So the idea is we want to develop a closed loop speech chains model based on deep learning. And at that time, it was the first that integrate the human speech perception and production behavior. So like this, not only human that have the auditory feedback, we hope also the machine can have the auditory feedback, so that the machine not has the capability to only listen or only speak, but also listen while speaking. Okay, so this is the conventional way where the ASR and TTS was completely developed separately and independent. And what we want to build is like this. So we give a feedback from ASR to TTS and from TTS to ASR. So this is the same way, like, so ASR will listen what TTS say, and maybe like the output of ASR also like give feedback to TTS. So TTS know what the ASR output. So then they can help each other. And so what is the benefit is that, so during the training stage, we can allow the training using label and unlabeled data as semi-supervised learning, where the ASR and TTS can teach each other using unlabeled data and generate useful feedback. So I will explain this a little more later. So during inference, we can use like a normal, I mean, we can use them separately, like a standard ASR and TTS. Okay, so a little bit more details. So X is the original speech and Y is the original text. X hat is the predicted speech and Y hat is the predicted text. So ASR here we use the seconds to seconds model that to transform from speech X to the Y hat, to the predicted text. And the TTS, also we use seconds to seconds model to transform from original text to the predicted speech. So if we have both pair of speech and text, so P here is the pair XP and YP, so we have pair data, then we can use standard supervised learning. So for ASR, try to map from speech to text, and then after that, given the correct text transcription, calculate the loss, backpropagation, and improve the model. In the same way, like TTS from text to speech, and then given the correct speech waveform, calculate the loss, backpropagation, and improve the model. Now, if we only have speech data, so what we do here, we give to the ASR to transform from speech to text, but here we don't have the correct text transcription. So then we give it back to the TTS to transform from text to speech. And finally, because we have the original, the beginning, the original speech data and the predicted of the TTS, then we can calculate the loss between XU and the predicted one, and then backpropagation. So here that meaning that it's possible to improve TTS with speech only by the support of ASR. The same way if we only have text data. So we give it to the TTS to produce a speech, and because we don't have a correct speech waveform, so we ask ASR to listen what TTS say, and then ASR try to predict the text based on that. And so because we have the original text and the predicted text from the ASR, we can calculate the loss and then backpropagation. So here it's also possible to improve the ASR with text only by the support of TTS. So the training objective we can adjust here. For example, we keep the training that we use with the pair data plus the unsupervised data, so it's become semi-supervised. Or we can lower the experience before when using the pair data. So this is just to keep the memory when we have the pair data, but you can adjust the alpha and beta. Yeah, so when alpha become more than 0 means that you keep some portion of the loss and the gradient provided by the pair of training set. Okay, so at the time we built simply using the sequence to sequence with for ASR and also for the TTS. And the TTS we didn't use any wavegun, we just used the simply Griffin limb construction. And so we try first using the single speaker data, which is LG speech. So we try to try several scenario. So for example, we have pair data only 30%, the other one is unpaired. And for example, unpaired 35% text only and 35% speech only, and then let the ASR and TTS help each other. Okay, so this is the ASR performance. In the top one is the baseline when we have only like 10% paired data, and we cannot do anything with the unpaired data. And the character error rate is 31.7%. But given with the speech chain where they ASR and TTS help each other, and the performance can drop to 12.3% until, for example, if we have 50% paired data while the 25% only text and 25% only speech, the performance can have like 3.5%, which is close to the one that have 100% paired data. While in here it's actually only 50% paired data. Okay, it's also for the TTS. So let me play. This is the main opinion score. So let me play the sound. This is when have the baseline 30% paired data only.
The pieces aren't the problem. They actually provide a solution.
And this is after with the speech aid where ASR and TTS support each
The
other.
pieces aren't the problem. They actually provide a solution.
And this is upper bound when they have 100% of paired data.
The pieces aren't the problem. They actually provide a solution.
Okay, so here we show that inspired by the human speech chain, we propose machine speech chain to assist semi-supervised learning that enable ASR TTS to assist each other when they receive unpaired data, which allow ASR and TTS to infer the missing pair and optimize the model with the reconstruction loss. Okay, so let me continue with the part 2. So if you see that before, we only show it with the single speaker data. So how this done with the multi-speaker data? So the previous one couldn't perform on unseen speaker. So that's why we try to handle voice characteristic from unknown speaker by integrated speaker recognition into the speech chain loop. So this is the original machine speech chain, and then we added here the speaker recognition to help for the multi-speaker data. So what we do here, the same way, similar as before. So if we have only speech data, so ASR will predict the most possible transcription, try to predict the y-hat. And then after that, we also give speaker recognition to provide speaker embedding. And finally, TTS tried to construct based on the text from the ASR output and speaker embedding from the speaker recognition. And then after that, we calculate the loss and backpropagation. And the same way, if we only have text data, then we first try to sample from, and then after that, TTS generate given the text and given the sample of the speaker vector. And then after that, ASR try to listen what TTS say and produce the text transcription. And then after that, we calculate the loss and backpropagation. Yeah, so the difference here now, in the sequence to sequence TTS, we have the loss function of reconstruction, speech reconstruction, and of speech. And then now we have the additional because of the speaker, which is the cosine distance between the original and the generate speaker embedding. Now we can test it on the multi-speaker. We use his on the Wall Street Journal. So okay, so this is the top one is the baseline when we have only the Wall Street Journal 0, which is only 16 hours per data. So this is our performance, like 17.35%, and this is the other performance by the other paper. And so if we have the total supervised training with the 81 hours of pair data, then it can have the error rate like 7.12%. Now, if we keep only pair with the 16 hours while the remaining is unpaired data, with the label propagation, we only can, so using the greedy is like 7.52 with the beam beep search is like 14.58 only. So it's decreased a little bit, but only like 3%. But with the speed change, we can drop to like 9.86% character error rate. Okay, so this is also for the TTS. So I will play for the baseline.
The business aren't the problem, they actually provide a solution.
And performance is not good. And then after
The business aren't the problem, they actually provide a solution.
and this is when we have full data.
The business aren't the problem, they actually provide a solution.
Okay, so we can show that we can improve the machine speech chain to handle voice characteristic, where TTS can generate speech with similar voice characteristic only with one short speaker example, and also ASR can generate new data by combination between text sentence and arbitrary voice characteristic from the TTS. Okay, so now the question is, can we apply this to like multilingual tasks? Like now we try to apply this to the code switching ASR and TTS. Okay, so code switching is a speaker switch language within conversation. So here we give an example of Japanese English code switching.
If I could make a suggestion, この議題についての討議を昼食までに終えていただければと思いますが。
Okay, many researchers work also on code switching, but usually they work either only ASR or only TTS. And there's a lot of approach here that you can see. And again, either they only separately only for ASR and TTS, and they also requires a lot amount of parallel code switching data. Now let's see how we do the code switching in the human conversation. So actually, we never learn code switching at school. There is no like code switching language learning, right? So we learn several monolingual language. So for example, we go to the language school of English language school, or we go to Japanese language school. And then after that, we just listen and speak in a multilingual environment. And finally, we speak code switching, right? So we never really formally learn in the school about the code switching. So then we try to propose the same way, like we try to build it using the monolingual, like we go to the school. So for the monolingual data, we have a pair of speech and text. Then after that, for code switching, we just let ASR and TTS to listen and speak and to support each other. Okay, so here the different, this is basic speech chain, and this is the previous multi-speaker speech chain with the speaker recognition. Now the difference is we just adding a little here component, which is the language ID, just to support for the code switching. So for the training process, as I mentioned before, we only have pair data of the monolingual data. So here we have monolingual English, Japanese, and Chinese, and we have pair data here. And after that, we let ASR and TTS just do the feedback learning. So here means that we have English, Japanese, and Japanese, Chinese, text only or speech only. And then after that, we try to also do the zero shot, like we don't have this Chinese English at all, but we will try to test it also for this code switching data. Okay, so the data is, we use the code switching BTEC dataset is the English, Japanese, English, Chinese, and Japanese, Chinese code switching. So the baseline here is completely only monolingual. Okay, so this is the baseline here is only monolingual, 25,000 of Japanese, 25,000 English, and 20,000 Chinese. And then we tested on the code switching. Here, the character error rate is like 14%, 16%, and 16%. And after that, we use the speech chains where given the text only or speech only code switching English Japanese or Japanese Chinese. And so the performance can drop from 14 to 11%, from 16 to 8%. And even for here, the red one means that we don't give it anything during training data, but it can give the performance also for Chinese English. And so the same way for if we give like English, Japanese, Chinese English, or Chinese English, Japanese English, so the performance can drop here. And the bottom one here is the performance when we have all supervised code switching data. So we have pair speech and text for English, Japanese, Japanese, Chinese. So you see from the here 11%. For if we have supervised training data, we can have like 8%, like close to 9%. Okay, so here we show that we can expand machine speech chains to handle multilingual code switching by integrating the language ID. Is also it's allow code switching ASR and TTS to learn each other without parallel code switching data. And it can maintain the performance in monolingual setting and improve also in the code switching test data. So this is another case like we try to build it for the ethnic language of ASR and TTS. So as I mentioned earlier that we have more than close to 7,000 languages that have not been covered, but those languages are very have few data available. So here we try to build a cross-lingual machine speech chain. And so the idea is that, so for us human, even sometimes like we don't learn the language directly in the school or textbook, but we just go to that country and then we just listen and speak, and then we can in the end we can say we can speak to that language. Now we want to have the same way like that. So then the idea, we learn the new language with machine speech chain. So here the case is we use ethnic language in Indonesia. So this is the map of Indonesia. We have quite a lot ethnic language there. So now we focus on the 4 ethnic language, which is Japanese, Sundanese, Balinese, and Bataks. And so yeah, most of those languages are under-resourced language. So what we do here is we have Indonesian language as a standard language in Indonesia, and it has quite a lot pair speech and text data already. So we built the ASR and TTS using the Indonesian speech and text data, and after that. Okay, so this is the step 1. So this is for the ASR and TTS using the both pair of speech and text data. And after that, we do speech chains on those ethnic language. So we just give so this the ASR and TTS here is built it on the Indonesian language, but we give other speech data like other ethnic language, and then let the ASR try to predict it, the text, and then after that given to the TTS, and then after that we calculate the loss and then improve the TTS. In the same way, like if we have only the text data, we give to the TTS to produce the speech and the speech of those ethnic language, and then let the ASR listen what TTS say to predict the ethnic text. After that, we calculate the loss and then backpropagation. So the data set here, for the rich resource language of Indonesian, we use the data. We have like 80 hours of speech. It's consists of 400 speakers with 84,000 utterance. And so we use 10% of the data as a test set and the remaining as a training set. And so for the under-resourced language, for the ethnic language, we have only 40 speakers, but 40 speakers for 4 languages. So we have 4 speakers for each language, and only 325 utterance per language. Is a very, very, very short data. So then we make 10% of the data as a test set, which is only 50 utterance per language, and the remaining 225 utterance is used for the unsupervised training. Okay, so this is the result of ASR. The baseline, this is the baseline of Indonesian. So it's only trained using the Indonesian data. When this model tried to recognize the Japanese, Sundanese, Balinese, Bataks, the performance is really bad. This is character error rate, so it's 100%, 90%, something like that. So then the first proposal is we give only text. So this is completely only text without speech of the ethnic language. It can drop from 100% to like 63% or 63, 70%, and 72 for the Batak language. And the proposed two is that from the baseline, we give the unsupervised speech only or text only. And again, it's dropped to like 30%, 27% for Balinese, and then 37% for Bataks. And this is the top line where we have the supervised of the Indonesian from the baseline, and then after that we also train the supervised where we have the pair of speech and text of those ethnic languages. So because the ethnic language data is very, very small, so that's why even the top line we reach only like 20%, 70%, and 50%. And then the same tendency for TTS, and this is the L2 norm square. The same way when we have for the Indonesian baseline, and then for the proposed when we give the unsupervised training with the speech only or text only, and then this is for the top line. Okay, so here we show that machine speech chain can be applied also for developing the ASR or TTS in ethnic language where no speech text pair data is available. And the way we do it, we pre-train with the one rich language. Here we use the Indonesian with parallel speech text in supervised manner. After this, we perform speech mechanism with only limited text or speech in those ethnic language that enable ASR and TTS to teach each other even without any pair data. Okay, so next I'll go to the multimodal machine speech chain. So in the early of my talk, I mentioned that most common way for humans to communicate is by speech. But actually, a language systems cannot know what is communicating without a connection to the real world by the image perception. And human communication is actually multisensory. It involves several communication channels, not only auditory, but also visual channels. And human perceive this multiple source of information together to build a general concept. So not only listen and speaking, but it's also we read and watch, and of course we have this auditory feedback. So each of these modalities share complementary behavior. So also in the brain science, it's found that brain process involved inside have found that visual cortex also use information gleaned from the ears as well as the eyes when viewing the world. So speech is not only heard, but also seen. And auditory speech is typically accompanied by concurrent visual speech. So this study found that, so they make an experiment like 4 syllables, and the participants will see these 4 syllables, one with the matching mouth, articulating syllables, and the other one with the still face. So the face is do nothing. And the figure illustrates that when it has the syllables with the mouth that articulating that syllables, there is a region that significantly activate in the audiovisual condition. But you may say that the idea of incorporating visual information for speech processing is not new. Yes, it's true. The audiovisual ASR, for example, have been studied for a long time. But most of those approaches are usually made by simply connecting the information, and this method requires all information from different modality available together. So, for example, in order to build speech recognition, audiovisual speech recognition, we need to have parallel speech, text, and image, right? But on the other hand, if we see human learning does not really rely on parallel data on all modality. So in one time, we only use books with the text and visual, and in another time we see the auditory that this person say this is deer, and you see that this is visual is a deer. So it's not always that all these 3 components have to be appear together. So therefore, we propose a multimodal learning without the need of multimodal parallel data. So the previous machine speech chains is already let us free from the need of large size of parallel speech text data, but it's still required to have large size of unpaired data. So we still need a lot of only speech or only text. And this study is limited only to speech and textual modality. And so therefore, we try to build not only speech and text, but also speech, text, and image. And what we want to see is that if, for example, so this is when we have parallel data, of course, we can build the standard ASR TTS. We can have for basic machine speech chain and also multimodal speech chain. And for text and speech only, for ASR, even we use label propagations only drop a little bit. So with the speech chains, we can improve a lot. And this is also can be done with the multimodal machine speech chain. Now, what we want to see is that if we don't have text and speech anymore, and we only have image only data. So usually we don't use this for ASR and TTS, and basic machine speech chain also didn't use it. Now in this multimodal, we want to still utilize this image and see the improvement. So what we do here, we design a closely knit chain architecture that connect the ASR, TTS, image captioning, and you can use image retrieval or image generation. And here we try to train in semi-supervised fashion, where each of these modules can assist each other given incomplete data. Now, the question is that, as I mentioned, if we don't have no speech and text data available anymore, and we only have image data, can we still improve speech recognition or not? Okay, so same as before, if we have pair data like speech, text, image pair data, then we can train the speech recognition, TTS, image captioning, and image generation separately using supervised learning. But now, if we only have speech, text, image data exist, but they are unpaired. So what we do here, in the left side, so this is given only image or speech data. So left side is the same as before. This is speech chain. We give the speech to ASR. ASR produce the text given to the TTS, and then TTS generate the speech, and then we calculate the loss, right? And so now, given the image, we give to the image captioning. Image captioning will generate the text, and the text given back to the image generation to generate the image, and then we calculate the loss. We call it this as a visual change. And if we have text data only, the left one is the same as speech chain. We give to the TTS. TTS generate the speech and let the ASR listen what TTS say and produce the text, and then after that calculate the loss. And here also we can give the text to the image generation to generate the image, and then after that give it back to the image captioning to predict the text and then calculate the loss. Now, what we concern here, if we only have single data axis. So what we do here, for example, if we have speech data, can we improve image captioning? So what we do here, if we have speech data, we give to the ASR. ASR will predict the text, and then we give to the image generation to predict the image, and giving back to the image captioning to generate the another predicted text. And we can calculate here the loss between the predict text from the image captioning and the predicted from the ASR, and then calculate the loss and improve the image captioning. And the same way, if we only have image data left, we don't have speech and text anymore, but we still want to improve ASR. So what we do here, we give to the image captioning to generate the text, and text give to the TTS to generate the speech, and speech back to the ASR to generate the predicted text. So then we can calculate the predicted text from the ASR and the image captioning here, and then back propagation to improve the ASR. Okay, so for the image captioning, we use here similar to show and tell by Xu et al. And for the image generation, we use attention gun also by Xu et al. For the data, we use Flickr 8K. So there are 8K images where 5 caption image and 65 hours of natural speech, multi-speaker English speech. And then, so we divide the scenario like this. So we have a multimodal pair. We have pair of speech and text and image only with the 800 image. And then we have speech text image, but they are unpaired, so they are uncorrelated. And this is, we have like 1,500. And then we have speech only with the 1,850 image, and then image only with the 1,850. And so this is the performance. Okay, so this is the top line where we have 6,000 pair data. This is the result of ASR, image captioning, TTS, and the image generation. Okay, so this is using semi-supervised with the label propagation. We start with the ASR like 36.35, and then after that, we, given this ASR, try to generate the text, and then after the retraining that using the label propagation, but because ASR is the performance is not good here, in the end, using the 1,500 pair data, the error rate is improved, not decreased. And then given the speech only, then even getting worse. But using the speech chain, so we start the same with the 36.35 and let the ASR, TTS, image captioning, and image generation help each other. We can drop to from 36.35 to 15.10%. And then the one that interesting is here, even we don't have speech and text data anymore, we only have the image only, we can still improve the ASR. So this means that ASR could still be improved even without speech and text data. Okay, so this is the overall. This is the standard ASR and TTS when they're separate, and this is when the original machine speech chain, and this is now the multimodal speech chains. So with the image only, we can still improve the ASR. So this is using different data like figure 30K. So we still can improve from 10% to the 7% error rate. Okay, so this is will be the last. This is weekly supervised machine speech chain. So usually when we so up to now, the speech chain always need a portion of pair data, right? So now here we discuss if completely no pair speech and text. So this is an image of, for example, someone talk in Japanese, like Mas, kijangnya ningen di. So the person doesn't know what this person say. But when we point to the image like kijang, and then he knows that this is a deer, so using the same image, we somehow can share the information. So here that when there are no prior knowledge, learning is still possible from the confirmation that both utterance are talking about the same object. So here we concern on the partial alignment of visual connected. So it's talking about the same image. And within the language, this is the speech and text. It's not pair. But because it's talking on the same image, there is partial that is partial aligned. Like this is deer and deer, the grass and the grass. And when we work on the cross language, it's also the same. So this is the speech of Japanese, and this is the text of English. So we have partial aligned, although not all is pair data. Not word by word is pair. So of course that the construction of the non-parallel data also has gained attention recently. We have in the voice conversion or text-to-text translation, but they are mainly on the single modality like speech-to-speech or text-to-text. In the speech-to-text mapping, the cross-modal is still challenging. We have the like speech chain that still need pair data. And also this SAR et al. Try to attempt to perform the dialogue act, but not really to generating the description sentence. So what we want to do here is we want to map speech to text mapping. We cannot say this is speech recognition because it didn't recognize word by word. It's just somehow to map from this speech to text with the semantically equivalent. So this is from the unknown and transcribed speech utterance to semantically equivalent text without any parallel data. So this is the overall structure. We use here the vector quantized variational autoencoder to transform from untranscribed speech to the text. And then after that, we have from the code discrete speech representation to the text and text to code using speech change mechanism. Okay, so this is the VQVIA. And here for the code to text, we use the partial align second to sequence. NMT that this is usually used for the machine translation, partial align machine translation. And then this part is the speech chain mechanism. Okay, so this is for the, if we just do random, the blue score is just 2. And when we have the ASR to train directly from this speech to the text, we have only like blue score 4. And then after that, we use the VQVIA, and then after that, code to text. And we can reach like 15 blue score. And finally, with the alignment, we can have like 17. And using the code to text cycle mechanism, we can also improve further. And this is, we do it for the single speaker and multi-speaker, and we get the signal. Okay, so This we show that we can do weakly supervised mapping tasks from untranscribed speech utterance into a semantically equivalent text without any parallel speech text data, while we utilize the pipeline of the VQVA and the code-to-text speech chain, where it's possible to produce more semantically relevant text. So this is the publication of the speech chain. So today I presented until the weakly supervised machine speech chain. We have recently also the incremental speech chain and also the dynamically adaptive machine speech chain. And maybe you can see from the interspeech paper. Okay, so thank you very much.
Thank you. Very interesting. It's been an exciting talk. So we now have time for questions. Anyone with a question, please raise your hand or take the mic directly. And please start the video so we can see who's doing the question. So I do have a question in the meantime. This is a general question because I got really excited about the fact that you can improve the results without paired speech and text data. But somehow in your experiments, I guess just for comparability reasons, you limit the amount of unpaired data that you use. And then I could imagine that if you had more unpaired data, the results would continue to increase. Right? So do you do any experiments where you increase the amount of unpaired data, say for different factors, and check whether they keep improving results or whether they plateau somewhere close to supervised?
Okay, so let me go to...
So slide 55 could be, so there's several experiments, but the one in 55.
5. Maybe first I will show this this one.
Yep.
This is when we try to okay, so yeah, this is we limit the pair data to 10%, 20%, 30%, 40% to 50%, and then after that we use this pair data. I think maybe you want to see whether, for example, if this 10% and then this is 10%, 10%, 20%, 20%, something like that, right?
So my question, yes, it's related, but in fact, you have no bound in the, well, no bound. It's much easier to get unpaired text and speech data, right? So you could go, for instance, in the row where you have 50% paired data, and then for unpaired, you could go up to, I don't know, 2 times, right? 3 times more. So
right. Yeah, I think the performance will improve further, but there is also like saturation after that. Some point.
Okay, so that was my question. So I understand that that it probably would saturate somewhere below the 100% per data, right?
Right.
Okay, thank you.
So I think, for example, like this is single speaker, right? So if the TTS cannot variate the way they're speaking, the ASR cannot learn more. So if the TTS can play more like different intonation or different speaker, then ASR can improve more. Then after that, they can play further, I think.
Okay, thank you. We have a hand raised. Oh, sorry. Amen, did you raise your hand?
Yes. Do you hear me?
Yes.
Hello. Thank you very much for this presentation. So we have 2 questions. The first one is about the code switching in the ASR. My question is if we have 2 languages or more, One that is from the left to the right, and the other is from the right to the left. Could we use the same method? This is my first question, and the second one, when you talked about the TTS in the, for the underrepresented language for the Indonesian case, did you choose the Indonesian language because it is close to the underrepresented language that you work on, or we can do the same with maybe English dataset? We use English dataset and then for other underrepresented languages.
Okay, so so the sound is a little bit. So I will try to repeat it whether I understand the first question. So first is about the code switching. You're asking about left to right, right to left. Whether, for example, this is from English to Japanese or Japanese to English. Is it correct?
In the same text, for example, we take English and Hebrew language. English and Hebrew language, or English and Arabic language.
English to Arabic language, okay, and then?
Yeah.
Ah, I see. So the Arabic is from the right to left, and English,
Yeah.
I see.
Yeah, exactly.
How the code switching Arabic, English Arabic happen? I think if like the main is the Arabic speaking, I think it will be from the right to left, and then the English word will come, right?
Yeah, right.
So so in our case, we will follow how the speed come first. So if like we just if even like the original Arabic right from the right to left, but here in the text we will just write it from the left to right. It's just like the flow when the speed started. But I think you may set up this specifically for this one, I think. Yeah.
Okay. Thank you.
And then the second one for the ethnic language, what is the question?
The question is, should the main language be close to the underrepresented languages, or we can choose anyone?
So actually, the Indonesian and the ethnic language is quite different actually, but the important here, still we experimented the one that have the phoneme set is close. So for example, if we suddenly, like I train on the Indonesian and then I do on the Chinese ethnic that have a tonal language, maybe the TTS cannot generate that one. But if as long as that the phoneme set is still the same, it's still doable, I think. It's still possible.
Thank you very much.
Thank you. I think we have time for another question, and so I see a question from in the chat. So, Ander, do you want to make the question yourself, or do you want me to speak up? Oh, it's a comment. It's not a.
At the text like the byte why
I think it's a
the...
comment. Yeah, a clarification about left to right, right to left. Yeah. Okay, so if there are no further questions, I would like to thank you, Sakriani. It's been a great talk, and I'm really excited. I'm not working on speech processing myself, but I'm really excited that you can. But we do some multimodal experiments ourselves, and I'm really excited that the image captions and image generation helps in speech recognition. That makes a lot of sense. So it was very inspiring. Thank you very much.
Thank you. Thank you very much. Bye.
Okay.